You need to, in your future jobs, interact in a team and be productive in a group. But groups should only be as big as you do interact with each other. If half of the class here would be one group, it would be pointless, because then it might be 1 or 2 or 3 people in that group who actually did the work, and the rest just ride on. So that's the point of groups. Practice teamwork, practice interaction, become friends or partners, or some colleagues with each other in that contacts, form networks, but still practice and still learn the stuff which you're doing. And so if there is something fishy with the groups, like people appear in 2 groups or things like that, that gives you real concern for me. That gives conduct level concern for me, because then I'm not really sure who participated how in this work. And cases in which the group number is exceeded, or people appear in 2 groups or things like that, I will probably refer to the conduct in order to figure out what happened and who really did that work. I'm not saying you cheated, probably not, but it's still something which warrants investigation, and that's what the job of the conduct people are for. My job is to teach you chemistry, to set the problems, their problem is to figure out that things are going straight and giving us feedback. So if I feel that there's something going on strange, there will be a referral. If you get a referral, it doesn't mean you're guilty. It's also like in the midterm, there might be referrals to conduct because maybe 2 exams next to each other had very similar answers on them. If that happens, it means that at least half the people I refer to are not guilty, or not responsible as they call it, because one was a source and the other was a person copying, correct? And the source, by and large, in most cases, is not guilty. But figuring out who was the source and who was the person copying is not my job. I let conduct do that. So if you receive a referral to conduct in that regard, don't feel desperate about it. Don't even think that I think you did something wrong necessarily. It is half the people, at least half the people get those referrals because they just were the source and not the person doing something wrong. Right. In many cases, conduct just finds, no, that was okay. That was just coincidence or something. And that's also fun. I'm happy about every person being clean. Moreover, when these things appear, they're appearing by the code name. I don't know your code names. Slowly I might learn your real names, but not your code names. And so I have no correlation between your face and you and the code name. And so I will not approach you in any other way just because you will refer to that way. Because I don't even know who was referred to. Yeah. Are there any questions? There is an announcement on really staying the group the right way, and I think that is obvious. Anything else? Okay, very good. Let me also say one last thing about, there was maybe some confusion about the number of partners in the group. No group can exceed 3 people. But now I think we're in week 5, if I'm not wrong. So by the end of this week, by the last homework you hand in on Friday, you have to have collaborated with a total of 5 people so far. If you haven't collaborated with 5 people over the past 4 weeks, then we are just not going to grade your homework until we get up there. So you will just get the points. Do collaborate. You need to learn to collaborate, to approach people. It's an important job skill. And in the very end, that's what we're preparing for you. That's what you pay me for. That I force you to prepare for a job. Okay, anything else? Any comments, any questions? TAs are grading, I know that. I've seen them starting on Friday afternoon. Harold, did you finish? Or
Almost, yeah.
Almost, okay. So probably by Wednesday or at the latest by Friday, you'll get it back. Even after it's graded, they need to be collated, need to be typed into an island and so on. There's a little bit more extra work than that. So there's actually quite a lot of work for the TAs and grading, and so it can take time. Tentatively, I'm not 100% sure. The real midterm, I suggest the Wednesday after President's Day, I think the 19th. Is that bad for any, is there any other midterm scheduled already? So I'm not 100% sure yet. I want to see this week still how I'm getting along. In progress-wise, I want to finish statistical mechanics by that time, so that it's at the break between statistical mechanics and kinetics. But that is where I'm shooting for the second midterm. The shape of the second midterm will be just exactly the same shape as the practice midterm. So same number of questions, same layout, obviously different questions. It will be cumulative, so it will go from the beginning of the class until that time. So it will repeat electrochemistry. Okay, with that, let's go back to what we found out about 2 weeks ago, almost. We realized from very simple working on the board over here of the gas molecule bouncing around in the box that there are 1/2 kT per degree of freedom of the molecule. And that comes from the simple gas equation, PV equals nRT, that we didn't really need anything more than that. We realized that that is per degree of freedom. And gas molecules have, by and large, 3 degrees of freedom. They can, well, at least as we consider it, this way, and that way. So 3 degrees of freedom. Each of them, of course, has the same energy. There's nothing special about any one of those. So it is 3/2 kT for the total kinetic energy of those molecules. So if I heat up the gas, then the heat capacity of the gas better be 3/2 K, correct? Because if I make the gas warmer, that's what I'm doing. I'm just putting more energy into the kinetic energy and into the speed of the molecules. They move faster, and that is that. Now, if I'm looking at the molar heat capacity, then I multiply my 3/2 K with Avogadro's constant and get 3/2 R. K times Na is R, the gas constant. And that is really what people find. These are measured values. So whatever we did on the board over here was as good as these are. As precise really as you can measure. So it worked. But that was for the noble gases, which are just atomic gases. Now if I'm looking at the diatomic gases, things get fishy. So if I'm looking at things like hydrogen and carbon monoxide and nitrogen, it looks more like 5/2 and not 3/2. And then if I'm looking at chlorine and bromine, which are even heavier, it gets even more complicated. There are more things going on. So we have to figure out what those corrections are about. We have to learn what's going on here. And of course, you probably know already what's going on. Helium, neon, argon, krypton, xenon are atoms can't rotate. There's no difference really if they were to rotate. But diatomics can rotate. If I have H2, it has 1 rotational degree of freedom this way and 1 rotational degree of freedom this way. Can't rotate this way because you still can't see it. There's no difference. But otherwise it does. So there are actually 2 more degrees of freedom, 5/2. That's what we're getting to. But I'm going ahead of me, so we should do that correctly. And The only thing what we can do in this class is equilibrium statistical mechanics. If we wanted to look at non-equilibrium situations, we are going to do that a little bit in the transition in kinetics, but not really. That's more complicated, and that would be part of it. If I were to teach this at the credit level, then we would have time. So, often people call equilibrium statistical mechanics something like statistical thermodynamics, which is kind of a wall, because thermal temperature really is not subject to statistics, but comes out of statistics. Anyway. Stable system. That is something you've heard many times over in the past. I think there's really nothing new. So whatever we are interested in is a system, what we are looking in is a system. The system can be in a certain state. The temperature in this room can be 70 Fahrenheit. That is a state of the system. But that is a macro state of the system. That is a state where I can experience on the macroscopic scale. I could also try to define the microstate of the system, which would be all the gazillion gas molecules in this room being at each one position in each kind of velocity speed. If I were able to do that, then I could define the microstate of this room. And whereas in the macrostate there might be temperature 70 degrees, temperature 71 degrees, temperature 72 degrees, there are countable numbers, but not very many of them for the macrostates. For the microstates, then there are gazillion, of course, ways of setting up this gas molecule might be over there, and so on and so forth. So there are many more ways of setting up the system. And that is what statistical mechanics is about. We have to figure out how many ways are there to set up the macroscopic state in order to determine the properties. Especially relevant, that is, if we were then ultimately to look at transitions between different states. But if you wanted to look at transitions between different states, they can be set up in a different way. Some of them might have many ways of setting them up. Some of them might have much fewer. And that affects entropy, and that affects all the different kinds of thermodynamic potentials. And so it's really relevant. In particular, in this class, we are going to look at a canonical ensemble. A canonical ensemble is one in which the temporal average and the ensemble average is the same, and that is also very closely related to something which is called the algorithmic theory, which we're not going to talk about more. So, if I'm looking at these gas molecules here in a box, I can look at them for some time and put the average for where they are, probably in a second, for each one of them, and what speed they have, that is given, or what velocity in x direction and so on. All those properties I could look at, and I'll certainly find some value for those. Or I could imagine I have many equal boxes of gas molecules, and then take the average out of those ones. If those two averages, the average of the one system as it evolves over time, and the average between the many systems, if those two averages are the same average, then I have the canonical ensemble. For instance, if I had an open system where gas molecules can run out of, I wouldn't have a canonical ensemble, because then if I watch the gas molecules run out of it, then the average of the number of molecules in the system will change over time. But if I were to compare many equal systems, that average, they all still have the same. So those two averages would be the same. So in a way, it requires that the system is closed in some sort, it requires a couple of other things as well. The people who developed thermodynamics and statistical mechanics really like Latin and Greek. And so for that reason, like ergodic theory or canonical ensemble. Especially they like that those people who translated it into English. Yeah, canon, like canon law is the way it's supposed to be. Something canonical is the way it is supposed to be. So we are talking here about an ensemble as an ensemble is supposed to be. That is what canonical ensemble is. Okay, canonical ensembles. We are only going to deal with canonical ensembles in some sort of closed system. There are more to it. There are people call it things called a great canonical ensemble, which then will release some of those requirements. But that's really not so. Next thing is another Latin word, equipartition principles. In a canonical ensemble, the equipartition principle is found. Meaning that all arrangements of atoms are identically likely to occur if they have the same energy. So if I have my gas molecules over here, where those gas molecules are in that box and how much speed they have, all combinations have the same likelihood as long as the total energy of them is the same. That is called equipartition. The probability is equally partitioned, separated out to the different microstates as long as they all have the same energy. So, if I were to look at billiard balls or so on a table, then equipartition principle would be valid over here. So no matter in which arrangement I'm looking at the balls, each of them have the same likelihood. So each of them have the same energy. So each of them have the same likelihood. But this state over here for the billiard balls, where one is supported by the others, is higher in space, and consequently higher in energy, because there's potential energy for the billiard ball to be up there, that has a higher energy, and as a consequence, that is not anymore equally partitioned. It has a different probability, likely a lower probability, because there is a higher energy. Does it make sense? So, in different words, you can then say the probability for the system to be in one particular microstate only is a function of the energy and nothing else. So the energy is the only thing which determines the probability for the system to be in one state. Then my averages are the same kind of thing which we had earlier with distribution function, except that now we have microstates and states are countable. Whereas in the distribution function, I'm looking about a continuum. For the gas particles in gas theory, I thought there's a continuum of different velocities and speeds they can have. But in statistical mechanics, we say they're actually countable numbers. I can count over all the states J and their energies Ej and make the average out of them by summing up the probability of that state J and the energy of state J. If I'm doing this one here, I'm getting the internal energy. The internal energy is the average of the weighted average of the energies in all the states J, which the weighing over here to make that average is done by the probability times the energy in the state J. Does it make sense? Anybody problem with this? Now, if we start out from this, now we said two things. Probability P only depends on energy, and the averages are done in this way. From that, we can derive a ton of things. And assume we have two systems. Let's see. Let's assume we have two systems. One system maybe with the balls, and those ones are cubes. And so this is system 1, and this is system 2. And in each system, you have a probability. This is probability in system 1 for the state, for it to have a state associated with energy 1. Really, I should write that more complicated over here. That is probably I should write that is the probability K, pk of the system 1 being in this state K. And I think on the online one I wrote it more complicated. But in the end that's just a lot of writing, and I think it's still evident what I mean if I'm writing this. So, if this were the case, then I can also look at the combined system, correct? I can combine those two systems. And then I can say the probability for the combined system, for the system consisting of 1 and 2, that depends only on the energy 1 plus the energy 2, if they're not in any way interacting. Then that probability has to be the probability for system 1 to be in the state associated with the energy 1 times the probability for the system 2 to be in the state associated with energy 2. The probability that the combined system is in one particular state, if it consists of those two non-interacting systems, is the probability that one of those systems is in one state times the probability of the other system to be in the other state, right? Now I can take the first derivative of this one by each of the energies. So if I'm taking the first derivative by the energy 1, the energy of system 1, then I'm getting P1 plus 2. And I need to take the first derivative of this, so the first derivative of that, and then of E1 plus E2. And the internal first derivative of E1 plus E2 by E1 is just 1, right? There's no factor in front of this one, this is 0. So there's just a 1, which I can see. And here I have the first derivative of the probability of E1 by that. And this one here doesn't change because it doesn't depend on the energy 1. But I could also take my first derivative by E2 of this. If I were to take the first derivative by E2 of this one, I would get the first derivative of the probability of this system, and again the internal first derivative is just 1, so I don't have that, and here I have the probability of the system 1, which does depend on E2, so this stays, and here I have the first derivative of the probability of system 2 by E2. Anybody fine with this kind of math? Now the reason why I do it in this math is that I can now say, oh, I can divide them by each other. If they're both true, if they're not all zeros, then then I can divide them, correct? And if I divide them, then these ones clearly cancel. And I have a 1 over here. And then I can separate my variables and bring these over to the other side. So I have the probability of system 2, the first derivative of it, which depends on E2, and I divide that by the probability of system 2 of E2, this portion, and that is the probability of system 1, first derivative of it, by the probability of system 1 loaded. Okay? Just separate the variables, if you wish, the probability of system 1 and the probability of system 2. Which, and in order for this one to be always true, even if I change the energy of system 1 without affecting the energy of system 2, the whole thing needs to be a constant. If it were not a constant, then if I change the energy of system 1, somehow the energy of system 2 has to change. And that's not physical, because they're next to each other, not interacting and so on. So this only works, the whole thing, if this here is constant. So then this one here, I'm forgetting about this one now. I'm just looking at this equation here. And then I can, maybe I'll stop. Okay, so I have alpha, and now I forget that it was system 1 and just say the system P. So I'm saying P prime of E is P divided by P of E, correct? Probability of E. I'm looking at system 1, but I don't want to carry my details on. It's really irrelevant whether it was system 1 or 2 where I'm looking at it. Now, that is then also dP by dE. The first derivative was this one, divided by P, correct? So, if I'm separating my variables again, I'll find that I have 1 over P dP, and here alpha times dE. And then I can integrate. Then I'm getting the logarithm of the probability equals alpha times the energy, and I need to have some integration constant C for this. Okay, then I can put the whole thing to the power of E, and the probability of my system equals E to the power of alpha times E to the power of C. Make sense? I hope. This one here, a plus and exponent and multiply it with exponentials. Yeah? Okay, if that is the case, now I have a formula for my probability. So just knowing that those are additive, I know already that my probability needs to be an E function of the energy. But I know something else about probabilities. I know about probabilities that if I sum up over all the probabilities, the sum needs to be 1. If I sum
over I, the probabilities in the state I, and if I sum over all of them, that needs to be 1.
Now the I's are the states and not the systems. So that's why I'm using small letters now and not big capital letters. So if I have one system, and if I sum over all the possible states that system can be in, then the probability needs to come to 1. At some state the system needs to be.
Okay, let's plug in. So I have sum over I, e to the power of alpha times e times ei times e to the power of c equals 1. Which I can also write, e to the power of c is 1 over the sum of I, e to the power of alpha times ei, right?
So now I know
what e to the power of c is.
So my integration constant I just defined right now. If I know what e to the power of c is, I also know what c is. So this formula here,
I just defined this one, which is now my probability is e alpha I sum over I e to the power of alpha ei. And in order to keep my energy straight, I'll say
I'm looking in particular at the probability Pj of the state with the energy Ej.
so. This was any kind of probability, then it's also the probability for the state J, which has the energy Ej.
Now, in the last step, I need to define what alpha is. And there's a lot of math to do that. I'm not going to bore you with that math. But if you wanted to do that math, you can use the same kind of math which we didn't do in the gas theory and find out that your alpha here equals -1 over kT.
So really what we are getting over here is that the probability for a system to be in state J is given by e to the power of minus the energy of that state J divided by kT, and the whole thing normalized by the sum over all the states I that the system could possibly be in, e to the power of minus the state ei over kT.
This is cumbersome to write, and we always have this extra index in there. And so people abbreviate that by Z. And Z is the canonical, meaning the way it's supposed to be, partition. You separate it into function. Most other languages it's just the sum of the states, but in English it's a canonical partition function. So the Z, the canonical partition function, this normalization of the probability, that is really the essence of statistical mechanics. Because it turns out, when we know Z, we know pretty much everything which we possibly would want to know about a system. We only need to know this normalization factor. And let me show why. If I want to know what is the internal energy of my system, then I
I know that the internal energy of my system is the sum over J Pj. Pj is e to the power of minus Ej over Kt divided by the sum over I e to the power of minus Ei over Kt, and then I still have my Ej over here times Ej. That would be the internal energy of my system. That all looks like a ton of sums, doesn't it? They're actually kind of related, and we can easily see that if we ask ourselves, what is the first derivative of dz by dt? If I were to do the first derivative of this one over here, you all like your first derivative, don't you? I first have my sum and the sum stays, and then I have the external first derivative of the e function. That stays, correct? E to the power of minus ei over kt. First derivative of the e function is an e function. Then I have the first derivative as an internal first derivative of minus ei over k times 1 over t. That gives me a factor of minus ei over kt. And then I have the first derivative of 1 over t. And the first derivative of 1 over t is minus 1 over t squared. So this is my first derivative of the canonical partition function. This here is a canonical partition function. This was z, right? This one over here looks very similar to that one in a way. I could write this one here as sum over I e to the power of minus ei over k t times ei, the minus and the minus cancel, and the k t, k, and kt squared can go in front because it doesn't depend. Now this one over here is the same as what I have up here. So this one here is, as a consequence, 1 over kt squared dz by dt, that is this, 1 over kt squared. Kt squared, I cancel this portion over here, and then I have exactly this one. So kt squared dz by dt, and in the denominator it's the z. So my internal energy is kt squared dz by dt divided by z. Okay, so I can write it just in terms of the canonical partition function z. People who developed statistical mechanics will love this first derivatives, and so they realize one more thing. If I have d ln z by dt, if I'm taking the first derivative of this one, then that is 1 over z. That is an external derivative of the logarithm dz by dt. Now that is exactly what I have over here. So people write this kt squared d ln z by dt. And now I have a really nice and compact way of writing the internal energy. It is kT squared dln(z) by dt. And it only depends on the temperature and the canonical partition function. So I have a way of expressing, once I know what my canonical partition function is, I can get the internal energy just written as a function of the canonical partition function. Next session we are going to see how we can also look at the other thermodynamic potentials. For today, I'd like to give you still some homework. And part of that is that you just use your gas theory. So the first question here is, in gas theory, which fraction of nitrogen molecules in ambient temperature have at least the speed of a person walking, and so on and so forth. That is, you look at speed, that is Maxwell-Boltzmann distribution, correct? So you would take doing gas theory over here. The second problem over here, you're viewing the barometric formula. You ask yourself, how big does a hot air balloon needs to be in order to carry 10 kilograms? Assuming that the hot air balloon itself weighs nothing. So its payload, including itself, is 26 kilograms. The next problem here is to roll a six-sided die, normal die. And you want to figure out what is its canonical partition function. And we're thinking about the state after you wrote it and it's on the table, not during the tumbling of the table, that's complicated. But after it came to rest on the table, then you ask yourself, what is this one here? This is the canonical partition function. What is that? You can actually evaluate that. You can get a number for that. What is that number for that? And the last question which you have over here, if you have the energy states follow a linear progression, meaning energy of state 0 is 0, energy of state 1 is 1, energy of excited state 2 is 2, and so on and so forth. Then you know the energies of the states, and then you can also figure out what the canonical partition function is. That depends on the temperature, so it's not a number, but a formula. But that formula can be derived really quickly as well. So that is your homework, those 4 things, and of course it will be available in our. Thanks so much.